So in this video, I want to fit a simple linear regression model to our data set where I'm going to use the on-base percentage difference, which remember is the difference between the on-base percentage of a particular team and their opponent's on-base percentage that they faced that year across all the opponents that they faced. And we saw that there was this linear relationship between on-base percentage difference and the win rate. We're trying to predict the percentage of games that a team's going to win in any given year based on how much more they got on base versus another team, the other teams that they played that year. And we saw that there was a strong linear relationship, or what looked like to be one, between on-base percentage difference and win rate, as well as slugging percentage difference and win rate. And they were really close, so I'm going to test it real quick to see what the correlation is between on-base percentage difference and slugging difference. The correlation between on-base percentage difference and win rate was 0.874, and it looks linearly correlated. Just to make sure that it's better than the slugging percentage difference. And as you can see, slugging percentage difference is about 0.85, 0.849, but it's a little bit lower than on-base percentage difference. And so we're going to use on-base percentage difference as our one, independent variable to predict the win rate at 0.874. So we have some missing data here in the data set. Missing data is not good for our models. Our models can't read them. There are more graceful ways to handle missing data than to just drop the rows where the data is missing. But we're not going to cover that right now. And I'm just going to drop any rows that have no on-base percentage difference, no slugging percentage or win rate. And you'll see how we drop down from 1,200 examples to like now somewhere around 400 and something. And I would like to point out I'm using slugging percentage. We're not going to use that for the simple linear regression case. I'm going to explain why I'm using slugging percentage in the multiple regression case. So this is some code right here to fit our model to the training data set. And as you can see, I have an R squared of about 0.76, but it's 0.755. Remember, R squared, you can think of it quite simply as the square of the correlation coefficient between the predictions that the model outputted and the actual values that the model was trying to predict. And we see we have a mean squared error on the training set of 0.0012. That means that the average squared error difference between the predictions and the actual win rates on the data set was 0.0012 difference, and that is very small. So we're getting pretty good predictions here. I want to output, for the sake of R squared, the actual relationship between the observed win rate, the one that actually is in the data that we got, and the predicted win rate, the one that we actually predicted. And as you can see, there's a strong linear relationship between the model's predictions and what was actually in the data set. And so R squared is going to be the correlation coefficient of this squared. And I just wanted to point that out, is that ideally, if we had a 100% accuracy, we predicted with the win rate exactly every time, these points would be lined up in a straight line, because if this was the win rate of 0.35, the model would have predicted 0.35, and if it was 0.4, it'd be predicting 0.4, and these would be lined up in a straight line, and the correlation would be 1, and R squared would also be 1. So let's move on to the test set, because we just evaluated on the training set. I want to evaluate it on the test set too, to see how it does on untrained data. And as you can see on the test set, it does pretty good. It actually does a lot better on the test set. On the training set, we got a 0.76. I'm going to round it up to 0.76 R squared. On the test set, we got a 0.80. And so we actually did better on the test set, and our mean squared error was lower on the test set.